Guys. So at this point, hopefully you're coming to grips with essentially my answer to what atoms look like. Or I should say the quantum mechanical answer to what atoms look like. Well, so basically we've got this idea that electrons exist in these orbitals, which are clouds or probability distributions that define regions of space around a nucleus wherein we're likely to find an electron. So with each one of these probability distributions or orbitals, we have a way of labeling these orbitals, namely the n, l, m sub l quantum numbers. Okay? We saw that each one of these orbitals has a size defined by that radial distribution function and a shape, right? And those shapes had, different types of forms, cloverleaf, dumbbell, here, and so on and so forth, as we went to different types of orbitals. Now what we're going to do is round out this conversation by basically answering the question of what types of orbitals are going to be occupied for a given atom. So to do this, we're going to have to talk about another characteristic that we haven't really talked about yet, which is this idea of electron spin. Now, I actually introduced this concept sort of behind the scenes in our electron housing analogy, where I said that if you are putting electrons, two of them, in a given room, they must be facing the opposite direction. Okay. What I was actually presenting to you there was a concept related to this fundamental property of electrons called spin. Okay, so spin, the name implies motion, of course. However, that is not actually what's occurring, right? And we're not going to go into too many details as to what this actually is. I basically want you to accept spin as a fundamentally quantum mechanical property of electrons. Okay, it's a form of angular momentum, which is why we call it spin. But it is a very unique quantum mechanical property, and we're going to have to leave it at that. But at some level, by asking you to just accept spin as what it is here, quantum mechanical property, and leave it at that, it's not too far off from what I've asked you to do when, say, presenting the concept of charge. All right, so if you really are asked the question, what is charge? Well, of course, charge comes in two varieties, plus and minus. And of course, you can have neutral, zero charge. But answering the question of, well, where does that charge come from, that's a very challenging question. And the only reason why you haven't really asked that one is because you've been presented the concept of charge so many times that you just accept the positive or minus description. Opposites attract, like charges repel, and move on from there. Well, I want you to sort of quickly get to the same point with spin. And basically, spin is a permanent property of electrons, just like charge, or just like the mass of that electron, and it does not change. Okay? And there's two different types of spin. Just like there's two different types of charge, positive or negative, there's two different types or two different flavors of spin. And we denote these by spin up with an up arrow right here, and spin down with a down arrow, okay? And they have a corresponding quantum number that allows us to identify each one of these two possible spin states. So the quantum number we're going to do here is the spin quantum number, m sub s, and it can take values of plus or minus 1/2. So if you have a plus 1/2, we're going to call it spin up. If you have a minus 1/2, we're going to call it a spin down, and we're going to represent those electrons with each of those respective spins by an up arrow and a down arrow, respectively. Okay, so if you accept that definition and existence of spin, then we're now in a position to go ahead and start answering the key question that our key objective for this section, namely, what orbitals are going to be filled or occupied by electrons for a given atom? Okay, so it turns out there's 3 rules that we have to follow, and we're going to apply these 3 rules to what we already talked about on our previous exploration. And again, if you can go back to those electron housing analogy, we talked about how as you go to larger and larger electron homes, higher and higher values of the quantum numbers, you get corresponding higher energy orbitals. Okay? And we could draw out the relative energies of these orbitals, and again, keeping in mind that those energies that correspond to each one of these orbitals are something else that is derived from our good old friend, the Schrodinger's equation. So once we have that layout illustrated on the top of the slide here that tells us the energy for each one of these orbitals, we can then apply these 3 rules that I mentioned and use these 3 rules to essentially come up with an electron configuration for any atom. Okay? So the first one of these rules is the so-called Aufbau principle. Okay? And the Aufbau principle says that we are going to place electrons in the orbital with lowest possible energy. So you can remember this by saying, hey, if you're rolling a ball down a hill, well, that ball doesn't stop until it goes all the way down to the bottom of the hill, the lowest possible gravitational potential energy, right? So it's sort of a natural principle in nature. Systems evolve to the lower energy configurations. So we're going to do the same thing here. So if I have a single electron that I'm putting in to this diagram up here, this electron orbital energy diagram denoted at the top of the slide here, I'm going to put that first electron in the lowest energy orbital, right here, my 1s orbital. All right? And then remember, also in that electron housing analogy, I talked about a housing rule that says that only 2 electrons, no more than 2 electrons, are allowed in any given room or any given orbital. And if you have 2 electrons in a given orbital, then they must be spin paired. In other words, one must be spin up and the other must be spin down. So if I were to bring in another electron to this diagram here, I'm going to put that electron according to the Aufbau principle in the lowest energy orbital that's open, and which is of course the 1s, but I'm going to have to face that electron down. It's going to be a spin down electron. Okay? And then the final rule comes down to essentially choosing where to place an orbital or an electron if you have orbitals that have degenerate energies or the same energy. So degenerate here means the energy. So let's do a quick definition box of that just so that you remember. It's a very common term that sometimes confuses students. So when I say degenerate orbital, all I mean is an orbital that shows up with the same energy, which means if I look at this energy diagram for each one of those atomic orbitals, we can see that for a given value of n, in this case n equals 2, all of those hydrogen orbitals with an n equals 2 have the exact same energy. So we say that all of those n equals 2 orbitals are in fact degenerate. And the same thing holds for n equals 3, and so on and so forth. So if we started populating the list and went higher and higher, for hydrogen, just for hydrogen, the energy of these orbitals only depends on n, and we saw a nice little equation for that. Okay, so now let's start looking at atoms that are more complicated than hydrogen, so-called multi-electron atoms. So in order to explore the electron configurations for multi-electron atoms, I want to turn our attention once again to the CDF simulation. Okay, so our interface here for the electron configurations basically allows us to control the number of electrons in our first slider bar here. So that's what we're going to look at first. We're given the first 3 levels and then our 4s orbital as well. And we're basically going to start putting electrons into this energy level diagram and start looking at the effects. So right now we're starting off with just a single electron corresponding to a hydrogen atom. So we can see, according to the Aufbau principle, we're going to put that electron right down there in the 1s orbital. Now, if we put in a second electron, as we saw before, we are going to again follow the Aufbau principle and put that electron in the lowest possible energy orbital, which in this case would be the 1s orbital. But now watch what happens. Going from just one electron to two electrons impacts the energy ordering of the rest of those orbitals. Okay? And so to use the vernacular, when we introduce a additional electron to form a multi-electron atom, we break the degeneracy of this n equals 2 shell energy. So now the energy of the s orbitals and p orbitals are in fact different. Okay? And so now, if we start building beyond hydrogen, say, or beyond helium in this case, and move on to, say, lithium with a third electron, now we get a very clear choice as to where to put that third electron. Go ahead and pause the video there for a second and try and predict where are we going to put a third electron according to our rules. So we're going to apply the first rule, the Aufbau principle, put in the lowest energy orbital possible. Well, Pauli exclusion says that we can't fit any more electrons in this 1s orbital. It's full, which means we're going to go up to our next highest energy orbital, which in this case is a 2s orbital. So when I put in my third electron, it's going to jump in right there in that 2s orbital. Then if we go to beryllium, right, we then have a spin paired electron joining the other 2s electron. And then when we go on from there to boron and then carbon, right, we're now starting to populate p orbitals. But notice, when we go from boron to carbon, I am putting those electrons in not the same p orbital, but in separate p orbitals. So remember, this is Hund's rule. So we've got boron, carbon, and nitrogen. Hund's rule says populate electrons in individual separate atomic orbitals before you spin pair them. And we can actually understand this by going back to our housing analogy as well. If you have an option of either moving into a house and sharing a room with a roommate or having your own separate room in the house, you can imagine it's going to be a lower stress, lower energy environment if you choose to take a separate room. Well, it's the same thing with electrons. Remember, all electrons are negatively charged, and so if you have two negatively charged electrons occupying the same region of space, the same orbital, then there's going to be a greater degree of electron repulsion. So if we have an option of putting those electrons in separate orbitals, we need to do it to lower the overall energy of the atom. So we can build up in that way, we can get all the way up to nitrogen, but then once we form nitrogen, we've populated all of these degenerate 2p orbitals, and so our 8th electron, corresponding to the number of electrons in an oxygen atom, is then going to have to pair up with one of the existing electrons in a p orbital. Now, I arbitrarily chose the px orbital to add the electron. That would have been energetically equivalent to put that 8th electron in any one of these 3 p orbitals. So then we can go up from there, fluorine, and then form our noble gas, neon in this case. So once we've hit neon here, now we've filled up all these orbitals. So if you want to go up here to sodium, then you're going to be starting to populate the next shell, the n equals 3 shell, and keep growing as we just did for the previous shell, pair them up, and then once we've paired up all of those p orbitals, then something rather interesting happens. Notice that this shifting in the relative orbital energies resulted in the 4s orbital actually having a lower energy than the 3d. So once we've filled up our 3s and 3p orbitals and we're putting in our 19th electron, that 19th electron is actually going to jump into a 4s orbital as well as the 20th electron before the electrons start going into d orbitals. So I encourage you guys to, once again, play around with this CDF, rewatch that little video, and get used to how you populate these energy diagrams. And remember, the whole idea here is nothing more than what we already talked about with our little electron housing analogy. We're just basically looking at higher and higher energy homes and populating those homes with electrons according to those same quantum housing rules that we talked about before. Now, the way that you can keep track of the order in which orbitals are filled, I mean, there's a number of different ways. And one of the ones that's oftentimes presented, in textbooks is this figure here from the OpenStax book, where basically you can write out all the S, P, and D orbitals, and of course just shift down one step, and then draw this, follow this little pathway here. That will then capture how you should go through and populate orbitals. Which orbital comes first is the one that simply has the lower energy. And again, that energy comes from none other than the Schrödinger equation. So the Schrödinger equation is giving us this orbital energy, orbital filling. All right, so now that we've covered the basics here, we really have a strong foundation for a lot of chemistry that we're going to be moving into throughout the rest of the course. And one of the first things we can do with the knowledge we've gained is actually make some sense as to why the periodic table is laid out the way it is. So hopefully at this point you're used to staring at the periodic table, and you've probably just accepted the layout and gotten used to it. All right, but if you looked at it the first time, maybe if you think back to the first time you saw the periodic table, a first question comes to mind as to, why does it have this, little staircase arrangement here, this flat region? Like, why are these atoms grouped in the way that they are? Well, if we look at the electron configuration as determined by these rules, these three rules that we've laid out on the earlier slide, we can see that looking at each one of the atoms in each one of the regions of the periodic table, we'll find that all of the atoms in this region right here, or alkaline earth metals here, all of these atoms have their highest energy orbitals that are occupied being s orbitals. Okay, so the highest principal quantum number orbitals that have electrons sitting around in them are s orbitals. Over here in this pink region, okay, helium is of course going to be over there with the 1s orbital, but all the pink region here, these guys are all going to have their highest energy orbitals being p orbitals, and this whole chunk right here in the middle have what are called our d orbitals. And so basically, when we go through the periodic table and we are grouping together these different elements, the different color schemes and these different chunks, these different regions, correspond to the types of orbitals that are occupied and that have the highest energy. Now, this is a really important concept, these electrons with the highest energy. And in fact, it has a special term, all right? We refer to these electrons that have the highest energy as so-called valence electrons, okay? And so these valence electrons, they're the ones occupying the outermost shell, the shell that has the highest value of n. So the highest n, highest principal quantum number we saw previously when we looked at the radial distribution function, corresponds to orbitals that have a higher probability of finding that electron further from the nucleus. In other words, they're bigger. So the valence electrons are basically the electrons that are in the largest or outermost orbitals. So denoted here in blue, we've got our high energetic, see they're up there singing with their microphone, electrons, and inside, all of those electrons in that inside region are called core electrons. So anything inside of that outermost shell is a core electron. So there can be multiple shells of core electrons, but there's only going to be one highest energy shell of valence electrons. Okay, so what we're now in a position to do is start to write down the electron configurations for any arbitrary element. Now, of course, we've seen that energy diagram, and we're able to follow our three rules, namely the Aufbau principle, Pauli exclusion principle, and Hund's rule, to allow us to populate that energy diagram. But it can be a little cumbersome writing out an entire energy diagram. So remember, writing something like this with our 1s, 2s, 2p, and so on and so forth, that's a lot of work, right? So we want to shorthand this process to avoid having to do all that extra work. And we're going to do that by using our notation that we developed previously for each one of these orbitals. And so if we're basically going to write down that notation and use a superscript to denote the number of electrons in that given orbital. And we're going to basically repeat this process until we've identified the orbital in which each one of the electrons in a given atom or element, in which the electrons for a given atom or element reside. So we're going to have a long list of all these orbitals with the corresponding number of electrons occupying each one of those orbitals. Okay, so if we play this game for sodium, we can go back to the periodic table, and I encourage you to follow along with that list, populate that energy diagram. We're going to be first filling up that 1s orbital, put 2 electrons in there, right? And we got to come up with a total of 11 electrons, so we're going to then put 2 in that 2s orbital. Then we're going to fill up completely that 2p orbital, and then that remaining electron is going to jump up to a higher shell. Okay, so using the terminology that we discussed on the previous slides, that highest energy electron in the 3s orbital is going to be our valence electron, and all of these guys down here in the 1s, 2s, and 2p orbitals are all going to be core electrons. All right, so by writing things out in this way, we're able to avoid having to write out this really complicated energy diagram. And we can make things even simpler by abbreviating this electron configuration by just writing out the noble gas, underlying noble gas that is closest to this element, and then just draw out the number of electrons in their corresponding orbitals that are beyond this noble gas. So for example, with sodium, our closest noble gas is neon, which has the 10 electrons that we actually denoted up here. And so the whole purple region is basically the electron configuration of neon, not helium, neon. And neon, we're going to put that in brackets to denote that we are talking about the electron configuration of neon, and then just write out the valence electrons. So to get some more practice writing out these electron configurations, let's go ahead and look at the entire third row of the periodic table. So we already wrote down sodium. We saw that sodium has this electron configuration of 1s2, 2s2, 2p6, and 3s1. So we can follow along the periodic table to make sense of this. We can start up here with hydrogen, and hydrogen's got 1 electron. It's going to go into a 1s1 orbital. Then we're going to come over here for helium, and it's going to put a second electron in that 1s orbital. Then we're going to come out here to lithium. We're going to have then a 2s1, and then beryllium will add in a 2s2. But again, beryllium has everything from below, so beryllium's electron configuration would be 1s2, 2s2, and then we're going to start populating the p orbitals. We're going to have a p, 2p1, 2, 3, 4, 5, and 6. So all of the atoms in this third row have an underlying core electron configuration of 1s2, 2s2, 2p6. And then when you come to sodium, we have that single electron occupying a 3s1 orbital. And then magnesium, you've got 2 electrons in an s orbital. Then we jump over here to aluminum and we start putting electrons in a p orbital. Then, silicon, we have 2 p electrons, phosphorus, 3 p electrons, sulfur, 4 p electrons, chlorine, 5 p electrons, and then finally argon with 6 p electrons. Now notice argon, it is a noble gas, so of course it would have the same sort of thing. We could now, as you start moving into the 4th row, use this electron configuration of argon to quickly reference the condensed electron configuration for 4th row elements. So proceeding in this way, we can come up with a periodic table, the valence electron configurations for every element in the periodic table. And actually what I want you guys to be able to do is completely fill out all of these electron configurations on this entire table. Now, I'm not asking you to memorize 100 different things. Remember, there's just 3 different rules that you follow here. And you just need to remember the ordering, the relative ordering of these different energies. So to get some practice doing that, let's work through a few example problems. So the first one I want to present is sodium once again, but I'm going to throw in a little curveball. Okay, we already saw that sodium has an electron configuration of 1s2, 2s2, and then you have a 2p6 with a 3s1. That's sodium. Okay, so this is our neutral sodium. But what we are dealing with here is a sodium plus. Okay, so sodium has 11 electrons. If we make that sodium into a cation, a positively charged ion, then sodium plus only has 10 electrons. So if we're writing out the electron configuration of this cation, then we have to remove one of the electrons. And we are going to follow our rules, and we're going to remove that electron from the highest energy orbital. So we're going to kick an electron out of that 3s1, and we're going to come up with an electron configuration of 1s2, 2s2, 2p6. In other words, we will have the electron configuration of neon. All right, so the common ion that is formed for sodium has the corresponding electron configuration of a noble gas. Okay, and this goes back to one of those key rules that you remembered from early on in the course. We remember that when we are forming ions, we are always adding or subtracting electrons such that that ion that is formed has an electron, the number of electrons that are equivalent to the nearest noble gas. And so now we have some quantum mechanical justification for this. We can use Schrodinger's equation, use these quantum mechanical principles to essentially calculate the energy of these anions and cations. And what you see by applying these quantum mechanical rules is that configurations, electron configurations that correspond to a noble gas are lower in energy and are thus the configurations that we are likely to see. Okay, now let's go on to our second example here, 10. Okay, so let's look at the periodic table. I don't expect you guys to remember where that guy is. So we're way down here with 50 electrons. So of course, once we move to this far down the periodic table, we absolutely want to avoid having to write out that complete electron configuration. You, of course, need to know how to do it, but for the purposes of this demonstration, we can use the condensed form. So what we're going to do is look at the closest underlying noble gas. And of course, that's this dude right here, krypton. So we're going to have an electron configuration for 10 that has krypton as its sort of underlying core set of electrons, and then we're going to be adding in electrons on top of krypton. So we're going to be adding electrons now to which shell? go ahead and pause the video and tell me which one of the shells are we going to be adding the valence electrons to. Okay, so to answer that question, we need to look at which row we are in. So the first row, n equals 1, right, we're adding electrons to the n equals 1 shell. The valence shell for the second row is n equals 2, n equals 3 for the fourth row, 4 for that fourth row, and n equals 5 for that fifth row. So the row of the periodic table tells us what that highest principal quantum number n is going to be. So we are now adding electrons first to a 5s orbital, because remember these first two columns correspond to s orbitals. So we're going to add 2 of those 5s orbitals, 1, 2. Then we have our whole stretch of d electrons. And remember from our orbital ordering scheme, energetically speaking, where the d orbitals are lagging behind by one principal quantum number. So if we're in the fourth or the fifth row, then we're actually filling the 4d orbital, and we're going all the way along the full stretch. And so we're going to be adding in an additional 10 of those d orbitals, and then we're going into the p orbital region. All right, so that region right here, the p orbital region, and we're back up to an n of 5, so we have a 5p, and there's 1, 2 of these electrons. Okay, so we can summarize those findings, and now we can move on to our next example, which is another ion, a phosphorus 3- ion. So going once again to our periodic table, we look at phosphorus here, and now we can perhaps shortcut this process once again. If it's phosphorus 3-, how many electrons is it going to have? Well, neutral phosphorus has 15, so if it's phosphorus 3-, we have an additional 3 electrons, which gives an electron configuration that corresponds to argon. And so we can, using our shorthand notation, actually just quickly write out the electron configuration for phosphorus 3- as an argon in parentheses. All right, now let's look at an example involving one of these transition metal elements. So going back over here, we can clear it off, and we can now find iron, right? So iron's going to be right here, and go back and use our same sort of shortcut approach. Shorthand notation, we're going to scroll back and say, what is that closest underlying noble gas? Well, of course, argon. And then we're going to move beyond argon, and we're going to start filling up first the s orbital, but now we're in the fourth row, so it's going to be 4s, and we're going to completely fill it up, 4s2, and then we're going to move into the 3d orbitals. Remember once again that those d orbitals lag behind by one principal quantum number, and we then need to figure out how many 3d electrons we're going to have. Well, we've got 1, 2, 3, 4, 5, 6 of these 3d electrons for iron. All right, now let's move on to our second to last example here and look at the electron configuration for F-. Well, at this point, you're hopefully feeling pretty comfortable with the process. So we look at fluorine, we are talking about an F- ion, so we're adding an additional electron. So we have an electron configuration that's equal to that of neon. Now for our final example, lithium plus, we're going to have our first cation that we've seen. So if we're looking at lithium, it's right down here with 3 electrons. But if it's lithium plus, that means we've got to take away one of these 3 electrons, which is actually going to move us back to helium. So we actually have an electron configuration of helium, of course the 1s2. 1s2 then would be our full electron configuration. All right, so that is how you write out electron configurations for any element in the periodic table, and we also examined some ions, in that S and P block region. So now would be a good time to go ahead and move through those practice problems regarding electron configurations, and then we'll cover our final video for this section of material, which will look at some more periodic trends in that periodic table.